Right. As always, we begin by looking at what we're being asked for and what we're being given. Here we want to know the mass percent of oxygen, and we're being given the molecule shown below. Alright, well, how to start? Let's think about what we're actually being asked for. The mass percent. How do we find a mass percent? Well, what we want to do is we want to find the mass of oxygen, and then we also want to find the total mass of the compound. Probably could have done a better job here planning that out. Okay, of compound. Right, and since it's a percentage, then we're going to take what we find and multiply by 100%. Alright, so how to start? We need to figure out something about the mass of oxygen and the total mass of compound. We're not giving anything about the total mass of compound, so we're going to have to make an assumption about that later. But first, before we do anything else, if we're asked to relate something about mass percentages and stuff like that, we're probably wanting to figure out something about the molecular formula. So let's figure out the formula first. Alright, what we see is we have 3 hydrogens, 3 oxygens, and a phosphorus. And so our formula is going to be H3PO3. Good. Now what we need to do is we need to somehow fill out this, the mass of oxygen, the total mass of the compound. But we're not being given anything. We're not told how much we have. Which means for us that we get to assume how much we have. And I like to make my life as easy as possible. Chemistry is done in moles, so if it were me, I would assume that we have 1 mole of compound. How do we figure out how much mass is 1 mole of compound? Well, we use the formula to determine the molar weight, right? And so what we have here is that the formula weight, or the formula mass, is just going to be the sum of adding up 3 hydrogens of phosphorus and an oxygen. And when we add up the total mass of that, what we're going to end up with is 81.99 grams per mole. Alright, but we've already assumed 1 mole of compound with this formula mass. And so together, what that gives us is that the total mass of compound is just equal to that formula weight, 81.99 grams. Great. At this point, what we've done is we've found the value that goes in the denominator of our definition of the mass percent of oxygen. What we need to do is find still the mass of oxygen that's present. Well, how do we do that? Basically, we use the formula that we just solved for to give us the information that we need. What we know, because we've assumed this, is that we have 1 mole of compound. So if we have 1 mole of H3PO3, and we want to somehow figure out how much oxygen we have, what we need to do is we need to get rid of H3PO3. So we're going to put that on the bottom. And we don't want to be in terms of moles. So we'll put that on the bottom. We want to be in terms of moles of oxygen, atoms. And when we look at our formula, right, what we find is that for 1 whole mole of H3PO3, we're going to end up with 3 moles of oxygen. That's what the formula tells us. It tells us for every mole of that compound how many moles we have of each of those atoms. And so what we can do is we can say 1 mole of H3PO3, put that on the bottom, gives us 3 moles of oxygen. Another way to do this, if we wanted to read the top and then the bottom, is to say 3 moles of oxygen are present in every mole of H3PO3. Alright, so all we have to do is solve this. We end up with 3 moles of oxygen. And we need to know the mass. That's okay. To find the mass, all we need to do is multiply by another conversion factor. We need to be not in terms of moles. So let's put a mole of oxygen on the bottom and the mass on top. Grams of oxygen. And we know that 1 mole of oxygen is 16.00 grams. So we're going to take 3 and we're going to multiply 16 by 3. That gives us 48 grams. And so now we have the answer for the numerator part of this question. Alright, all that's left then is to take those two values and divide one by the other. And so we have 48 grams of oxygen over 81.99 grams of compound. Since we're working in percentage, we just multiply this by 100%, and what we find then is 58.5%. That's the answer that our analysis gives us. Then we just look at our answer choices. This one is awful close enough that on an exam I would be perfectly confident that that's the right answer. So again, just to review, all we did was we decided what the formula was, and then we used that formula to give us all the information we would need in order to solve this problem. Moving on to our next problem, we can ask ourselves, what are we being asked for? What are we being given? All right, we need to know the mass of hydrogen in a particular sample, and then we're given some information about that sample. Basically, we're told its molecular formula, all right, and then we're told also how much oxygen it contains. So how do we analyze this? Again, the key lies in the chemical formula. This chemical formula gives us all the information we need to know about how the atoms within our molecule of caffeine, what the ratio between those are, so that if I'm given any information about one of these atoms, like oxygen, I could convert that into information about any of the other atoms, like hydrogen. And so what we're going to do here is we're really just going to create a long mathematical problem where we use the chemical formula to provide a series of conversions for us in order to move from how much oxygen we have to how much hydrogen we have. Okay, so let's start. We'll take what we're given. Basically, we're given 0.325 grams of oxygen. We need to move that into grams of hydrogen. What do we do? Well, milligrams. Let me just fix that. Okay, milligrams of oxygen. What do we do? Well, okay, when we think about a molecular formula, these numbers in the molecular formula are telling us the mole ratio. And so what that means is if we're ever going to convert from one element to another or from an element to the molecule as a whole, we need to be in terms of moles. So the very first thing we need to do is convert our oxygen to moles of oxygen, right? So we're going to take mass of oxygen, we're going to turn it into moles of oxygen. That's not too hard to do. We know how to relate mass in moles. Basically, we know that 1 mole of oxygen, since we want to be on the top, has 16 grams of oxygen in it. Alright, that's nice, but we can see that we start with milligrams, and here we have grams, so that's not in agreement with each other. And so we also need to convert from grams to milligrams, or from milligrams to grams. So let's get rid of milligrams. We do that by putting milligrams on the bottom. We need to be in terms of grams on the top. And so what we know is that there are 1,000 milligrams for every 1 gram, and that's our conversion factor. We can cancel things out, right? Here's milligrams and milligrams, grams and grams, and so you can see that we're now in terms of moles of oxygen, which is where we needed to be for this first step in our problem. One thing I want to comment on is that you can see that we put in this conversion from moles to grams first and then grams to milligrams. It doesn't matter that we did that because the math still works out and everything cancels out in the end. For some people, it might make more sense to convert from milligrams to grams first and then from grams to moles. It really doesn't matter as long as all the units cancel out, which is why we need to put down units when we solve these types of problems. Okay, so now we're in terms of moles of oxygen. We need to get 2 moles of hydrogen. How do we do that? Well, we use this chemical formula to tell us everything we need to know. We know the relationship of oxygen to hydrogen in this chemical formula, and we can use those numbers to just write out a conversion factor. So, again, we are in moles of oxygen. We don't want that, so we'll put moles of oxygen on the bottom so that they cancel out. And we want to be in moles of hydrogen, so we'll put that on the top. Then we just look at our chemical formula and we directly read off what the relationship is. From here we see that there are 2 moles of oxygen for every 10 moles of hydrogen. And so we put a 2 next to the oxygen, moles of oxygen, and a 10 next to the moles of hydrogen. Now we can cancel out moles of oxygen and moles of oxygen, and we're left in units of moles of hydrogen. When we look at our answer choices, however, we see we need to be in terms of mass. And so now let's convert from moles of hydrogen to mass of hydrogen. That's not too difficult. We know how to get from moles to grams. So 1 mole of hydrogen is going to be 1.008 grams of hydrogen. That lets us cancel out the moles of hydrogen. We're now in terms of grams of hydrogen. But again, we can see our answer choices are in terms of milligrams. And so we have one last step, which is to convert from grams to milligrams. Okay, so we need to have grams of hydrogen on the bottom and milligrams of hydrogen on the top. We know that we actually don't even need the hydrogen part. We can just convert from grams to milligrams, and so there's 1,000 milligrams for every 1 gram. Good. Now what we can do is we can cancel out grams, and you can see that our answer is going to be in terms of milligrams of hydrogen. So now all we have to do is run this calculation. When I do that, I end up with 0.102 milligrams of hydrogen. When I look at our answer choices, we can see that that corresponds to answer A. And so again here what we're doing is we're using the chemical formula to give us the specific relationship between atoms. In particular, this chemical formula gave us this conversion factor because the subscripts in the chemical formula give us the specific molar ratios between atoms within a compound. Alright, our last problem is a combustion problem. We can look at that and see what's being asked. We really want to know the molecular formula of vitamin C, but we're really just being asked for the molecular formula. That's fine. What are we being given? Well, in a combustion problem, there's a lot of information actually that we have to be aware of. We're being given the fact that there's only carbon, hydrogen, oxygen. We know that it has a molar mass of so many grams per mole. We know that we burned so many grams. We know that we got CO2 and we know that we got so much water out of the deal. All right, so what I would do is think first about the reaction. We have vitamin C, and we even know how much we started with. We know we have 1.000 grams, 1 gram. We're going to burn it, which means we combine it with O2, and we know that this compound has carbon, oxygen, and hydrogen only, which means that all we're going to get out is CO2 plus H2O, and we even know how much of this we got. So we know that we have 1.50 grams of CO2 and 0.410 grams of water. All right, so now we've diagrammed all the information that we've been given. The key to analyzing this sort of problem is to realize that all the carbon that's present in the CO2 has to come from the vitamin C. Not only that, all the hydrogen that's present must come from the vitamin C, because the only thing that we're adding is oxygen. And so what we want to find is the number of moles of carbon and the number of moles of hydrogen that were present in the original vitamin C. That's not too hard to do, because all the moles of carbon we have at the end and all the moles of hydrogen we have at the end come from vitamin C. So let's just figure out how many moles we have at the end for each of these, and that'll tell us how many moles we started with. So let's do that. Let's think about moles of carbon. Well, right now we know that we have 1.50 grams of CO2. If we want to work in moles, the first thing to do is to convert to moles. So we have to somehow get rid of grams of CO2 and move into moles of CO2. We can do that by figuring out the formula weight, or the molecular mass, of CO2, which when we add up the atoms is 44.01 grams per mole. That's 2 16ths from the oxygen plus a 12 from the carbon. Alright, so then we have 44.01 grams of CO2 for every 1 mole of CO2. What that gives us then is something in terms of moles of CO2. We need, though, moles of carbon. So let's convert from CO2 to carbon. We can put moles of CO2 on the bottom and then moles of carbon up top. And if we look at the molecular formula, we see that for every 1 mole of CO2, we're going to have 1 mole of carbon. Now we can run this calculation, and when we do so, we have 0.034 moles of carbon. Great. That's the amount of carbon that we started with. We can do the same thing with moles of hydrogen. Same exact process. We need to know how much water we have at the end, or because that's where all the hydrogen comes from. That's 0.410 grams of H2O. We need to get out of grams of water into moles because we need to work in terms of moles. And so basically we know that water weighs 18.02 grams for every 1 mole of water. That lets us cancel out the grams of water. We're stuck now in moles of water, but we need to be in moles of hydrogen. And again, what we're going to do is we're just going to divide by the moles of H2O, and we're going to put moles of hydrogen up top. And when we read the chemical formula, we see that for every mole of H2O, we're going to have just 2 moles of hydrogen. And so we can write that down. 1 mole of H2O contains 2 moles of hydrogen. Then we can run this calculation, and what I get is 0.0455 moles of hydrogen. That's what we started with. That, again, both of these values come from the fact that we burned vitamin C. So the only place that carbon comes from is the vitamin C. The only place that the hydrogen comes from is the vitamin C. Great. So now we know the number of moles of carbon and the number of moles of hydrogen that we started with. What we can do then is try to put that into a molecular formula. How do we do that? Well, what you want to do is you want to identify which one of these two have the most number of moles present. In that case, clearly the answer is the moles of hydrogen. And so what you want to do is divide each one of these by the largest number of moles present. Alright, so now we're going to find the molecular formula, or the empirical formula, this way. What I'm going to do is, to avoid confusion, I'm going to erase the work we've already done. I want to make that a lot bigger. Okay. Right? We already found out these moles of carbon, and we already found out these moles of hydrogen. So we're just going to leave that right there. Alright. And now what we want to do is we want to take that value and divide by the largest value, 0.0455. And we do that both places. What is this going to give us? It's going to give us the ratio, basically, of hydrogen, of whatever atom we're looking at, to hydrogen. Obviously, when we do this, we have 1. When we divide this carbon, I'm sorry, I really messed this up. What you want to do is divide by the smallest number. Oh, good Lord. Okay, so 0.034 and 0.034. Yep, so you divide by the smallest number, we get a 1 here, and then when we divide here, we're going to have 1.34. Alright, the next step is to figure out how do we get to the smallest whole numbers possible. For me, the easiest way to do this is just to ask myself what I have to multiply by. Here I tell that if I multiply this by 3, I'm going to end up with a value of 4, just about. Here, if I multiply by 3, I'm going to end up with a value of 3. So what's this telling us? It's telling us that for every 3 carbons, we have 4 hydrogens. And we have the start of a molecular formula, right? We can write carbon 3, hydrogen 4. What else we know, though, is that there's some oxygen present in this sample. And so we also have oxygen, X, where we don't know what X is. But we're getting pretty close. So, what to do now? We need to revisit this idea of the burning process. We already know that all the carbon that's present and all the hydrogen that's present came from the vitamin C. So, let's figure out how much carbon and how much hydrogen there really was. Alright, good. Well, we know something. We know how many moles of carbon there were, and we know how many moles of hydrogen there were. And so let's just go ahead and figure out what the mass is. Alright, in order to convert moles to mass, what we need to do is we need to put moles on the bottom. We know that 1 mole of carbon is 12.01 grams. For the hydrogen, we know that there are 1.008 grams of hydrogen for every 1 mole of hydrogen. Good. We can multiply these together then. 0.034 times 12.01 is going to give us a value of 0.008. And then when we multiply 0.0455 times 1.008, we end up with 0.045. What does that mean? This is the mass of carbon and hydrogen that was present. Everything else has to be what? Well, the only other element present is oxygen. Which means that if we take these values and we subtract how much of each element there was from what there actually was, 1 gram, what's left over must be how many grams of oxygen there were. So we take 1, we subtract 0.408, we subtract 0.045 from that, and what we find out is that there was 0.547 grams of oxygen, because we've already accounted for the grams of carbon and the grams of hydrogen. We can then take that value, how much oxygen we have, and we can turn it, just like we did before, into a mole. And so here what we know is that there are 16.00 grams of oxygen for every 1 mole of oxygen. We can run this calculation, and we find out that the number of moles present is 0.342. Alright, just like we did here, it's getting a bit cluttered, I'm sorry about that. Let's see if I can get a different color out. Alright, here what we did was we wanted to have a ratio where we divided by the smallest moles. It's still in this case 0.34, and so we can take this number of moles and we can divide them by 0.34. And that process gives us a 1. And that 1 is our value of x over here. So now we can add that in. Whoops, there we go. We saw that what we would do with that 1 is we would multiply by 3 to give 3. So we're going to really put a 3 there. Okay, this is then our complete empirical formula. It's not our molecular formula, though, maybe. What we need to do is figure out the formula weight. For the, we'll call it the formula weight. Call it the mass. Right? Because in our problem up here, that's one thing that's given to us. The molar mass, or the formula mass. So, let's see what happens when we do that. We can add up 3 carbons, 4 hydrogens, and 3 oxygens. And when we do that, we see that we have a mass of 87.05 grams per mole. That is not the formula mass that we were looking for. Right? Again, the formula mass is given to us as 176.12. So now the next step is, and we're almost done, is to take this empirical formula and turn it into a molecular formula. And the way to do that is to take the mass of our empirical formula and compare it to the mass of our molecular formula up here. So let's go ahead and do that. I'm going to have to erase some more things. We'll get rid of this. Alright, and so what we find is that if we take our molecular formula and then we divide it by our empirical formula, it'll tell us how far off we are. So we have 176.12 grams, and for our formula mass, it's given to us right there. And then we take our empirical mass and we plug it in there, and that was 87.05. When we do that, we find out that we have an answer that's about 2. What that means is that our empirical formula, what we found down here, is 2 times too small. The actual molar mass is twice as big. And so all we have to do is that we take that number, 2, and we multiply each one of these numbers by it. So we multiply each one of those by 2, and then our formula is going to just be C6H8O6. And we can find that, hopefully, A. Perfect. Alright, and that's the answer. So I want to say 2 things real quick. This seemed quite long. That's because we try to go through it in extreme detail. The key to these types of problems is that all the mass that you observe must come from the original compound that you burned, except for that of the oxygens. And so once we figure out how much we have of everything, we can subtract that mass out and figure out what's left over. The other thing I want to say is on a test, this might take a long time, but you could also save some time because you know what? You know the molecular mass. And so you can just check each one of these to see which one of those agrees here. If you find only one, you have your right answer, and it probably took you about 2 minutes. If you find one or more, now all you have to do is enough of these calculations to see which one might be right. And all you really need to know is to distinguish between those most of the time is the relative ratio between the carbons and the hydrogens. So you don't have to go through the steps to get to the oxygens, and that can save you some time. But here we did the whole thing in excruciating detail. Not always necessary.